Hello, good morning, good afternoon, good evening, whatever time zone you are in. Welcome to another episode of the Bay Area Apache Spark Meetup Group. My name is Jules Damji. I am the technical staff here as part of the developer relations team, focusing on the open source projects. And today we are coming live to you on LinkedIn, YouTube, and X. And the recordings of this particular episode are going to be available for you on our YouTube OS Apache Spark channel. So if you missed it, if you want to share it with friends, go ahead and do so. Just a couple of logistics here for today. We can't really hear you. Slides are not advancing for some reason. We can't hear you. So if you have any issues with the video or audio or slides, please let us know in the chat so we can actually adjust and make sure that we remedy or address the problem. And keep your questions coming. If you are hailing from different parts of the world, please say hello on the chat so we will know where you're from. And keep your questions coming. We'll try to address the questions towards the end. We'll leave about 15 minutes or so. And any questions that we can't answer today live, we'll try to address them post meetup at the channels we have. Joining me today is obviously my esteemed guest, Carly, who's in the background doing all the magic so we can come to you live. And we have Eric and Gara. Say hello to the community, both of you.
Hello.
And just a little bit of background of my esteemed guest, Eric Ondenlik is the senior manager at NVIDIA, focused on the GPU-accelerated. So you're going to hear a lot about that today. Prior to joining NVIDIA, he was a researcher at Yahoo and HP Research Labs, and he holds a degree, a PhD in electrical engineering from Stanford University. And Gera Shagalov is a principal system engineer on the NVIDIA Apache Spark ETL acceleration team, which you will hear a lot about it today. And prior to joining NVIDIA, he worked at Twitter and database, where he gained a lot of experience at how to do things at web scale. And he holds both a master's and a PhD in computer science from Saarland University. Now, a couple of things that I want to sort of share with you about the upcoming events. We have several events which are sort of Spark related and how Spark fits into the grand scheme of Lakehouse to build your AI infrastructure. So on October the 30th, we have a webinar that you can actually register, where we talked about, the failed promises of how data lineage can be actually maintained at scale. On November the 13th, we actually have an open Lakehouse AI mini summit in Mountain View. So if you are living in the Bay Area and you're able to actually reserve that half-day summit, please do join us. And we'll be ending that with the Apache Spark happy hour, so you can actually come down, fill some sparks, share some drinks, and meet the committers and contributors in the community. So that's going to be in Mountain View, starting from 2 p.m. till about 5, and ended by happy hour. We also have a couple of virtual webinars, which are on November the 24th in Paris. So if you are in France, or if you want to join live, you can register that event, that particular QR code. And finally, very much related to today's talk, GPU-accelerated Spark data processing and meta management for GenAI workloads. Again, from the NVIDIA team, do register for those events and hope to see you there. With that said, I'm going to hand it over to our esteemed speakers to get started. So, Gara, you're going first, right?
Yes.
Okay, brilliant. And I'll just go off the camera here for a while.
All right. Hello, welcome to our meetup talk on Spark Connect with for GPU-accelerated Spark SQL and MLlib. My name is Gara, and I'm co-presenting with Eric. Our agenda today includes a brief introduction and background with motivation for GPU acceleration, as well as Spark Connect that can further simplify access to GPU acceleration in Spark. We conclude with presenting some benchmark results, and if nothing goes wrong, a live demo of a mortgage delinquency prediction pipeline. It features complex ETL for data preparation and feature engineering, followed by MLlib logistic regression. The demo uses Apache Spark 4.0 GPU accelerated by the Spark Rapids plugins in version 25.08. So from the macro level perspective, the reason why we're talking about accelerated data processing is that the studies such as the IDC Global Datasphere 2023 project compound annual data growth at a rate of about 28% per year. This boils down to hundreds of zettabytes generated annually. We believe that traditional hardware is not sufficient to sustain analytical and ETL data processing needs, and that only GPU accelerated compute can help us keep up with that growth. And as we know, Apache Spark plays a big role in big data ETL, hence Apache Spark 2 needs a GPU acceleration. So let's review the history of innovations in Apache Spark that lead us to today's talk. Already Spark 3 enabled some key functionalities. First, we got columnar batch processing, which is a must on modern hardware. Second was the ability to schedule tasks and on additional resources such as FPGA, and most relevant for us is, of course, GPU. Third was a way to plug in alternative SQL execution engines via Spark session extensions and Spark driver and executor plugin APIs. These innovations made Rapids Accelerator for Apache Spark possible. Acceleration is achieved without any code change to the application. Spark Rapids works with all common cluster managers, Spark Standalone, Yarn, and Kubernetes, and it is integrated with a number of Spark distributions and cloud service providers, and you see some examples on the slide. The plugin itself builds on top of another NVIDIA open source project called Rapids, specifically the C++ library libqdf, which powers GPU-accelerated Pandas API and other data processing engines. More recently, Rapids Accelerator for Spark has been extended to also provide acceleration for the Spark MLlib API. The MLlib Accelerator is built on top of another Rapids project called QML, which is a GPU version of scikit-learn. Both ETL and ML Rapids Accelerator for Apache Spark are open source and can be found on GitHub under the NVIDIA org. And build artifacts like jars and pip packages are available in the corresponding repos. Now, let's turn to Spark Connect. Spark Connect was introduced in Spark 3.4 and provided a way to run Spark SQL and data frame applications over gRPC. It separates non-JVM apps, such as the ones written in Python, through lightweight gRPC client from the JVM-based runtime on the Spark cluster on the server side, and these two are hard to maintain together. Using gRPC enables easy implementation of new language bindings for Spark in non-JVM languages, such as Go, Rust, or Swift. In Spark 4.0, we finally have the extension of the Spark Connect protocol to cover the MLlib functionality, which Eric will cover in greater detail in his part of presentation. So we can already guess why Spark Connect and GPU-accelerated compute is a great fit. As shown on this slide, we can keep the client app environments on the left slim and unchanged while managing non-trivial dependencies for GPU, CUDA, Spark, and other compute parts on the right-hand side. Now that we decoupled apps like notebooks from those heavyweight dependencies, we have the benefits of the accelerated compute on the one hand and the ease of maintenance of user-facing applications on the other hand. Application clients in Spark and CUDA runtime side no longer have to be upgraded in lockstep. In the following slides, we are going to take a closer look how it all works. Let's first review how data frames work over Spark Connect without GPUs. On the left is the client running some simple SQL and data frame application code. the application first connects to the remote Spark Connect server using gRPC. When executed on the client side, the Spark Connect client converts Spark SQL queries data frames to an unresolved logical plan. Spark actions now result in unresolved logical plan sent over gRPC to the Spark Connect server. On the Spark Connect server side, the logical plan is resolved into an analyzed logical plan, which is in turn optimized and converted to a physical plan. A tiny snippet of the physical plan in this example is shown in the light blue shade and contains some hash aggregations. In short, Spark Connect server acts as a Spark driver for a remote client, and the physical plan is then executed by the Connect server Spark application, and the result is converted to Apache Arrow and sent back to the client using the response part of the gRPC protocol. So now if we introduce Spark Rapids, our plugin for ETL on GPU, the accelerator is able to plug in on the server side at the physical plan level. And it basically takes every CPU operation that we know how to execute on the GPU into a corresponding GPU operation. And so the physical plans are equivalent. And so usually the ones that run on the GPU are prefixed with everything else is mostly the same. We use Spark for task scheduling and parallel execution. The most important point is that the client-side application code is exactly the same. No changes are required to the code. And herewith, I'm handing it over to Eric to continue with the Spark ML execution through Connect, and I hopefully will be back with the live demo.
Hey, thank you, Gara. Now let's take a look at how CPU-based Spark ML over Spark Connect, recently introduced in Spark 4, works. On the left is a simple Spark ML application that similarly connects to a remote Spark Connect server, as in the SQL case. The execution of the application code on the client, as in the non-ML case, computes an unresolved logical plan to represent the data feeding into the ML action, in this case, k-means fit. The plan and the ML parameters, including the algorithm and action being invoked, are serialized and sent via the gRPC protocol to the server. The server deserializes everything and resolves the logical plan into a data frame, along with the Spark MLlib classes and methods and parameters. In this example, the fit method is invoked on the k-means estimator class on the resolved data frame. The resulting model is cached locally in the server, and an ID identifying the model is returned to the client in case it needs to reference it for other operations, like getting the cluster centroids in this case, or doing a transform predict operation on new data. Let's look at the accelerated case. The Spark Connect server is now attached to a GPU-accelerated Spark cluster, while everything stays the same on the client side, just like in the SQL case. That is, no application code changes needed, and the messages flowing back and forth between client and server are unchanged as well. To leverage the attached GPU-accelerated Spark cluster for ML, on the server side, there is a plugin mechanism for ML that allows replacing the baseline Spark MLlib functionality with accelerated counterparts. The materialization of the data frame for ML computations leverages the accelerated physical plan execution by the Spark Rapid SQL plugin as before. So now that we have a basic understanding of how GPU-accelerated Spark Connect works from the application user point of view, let's look at server deployment from the service provider perspective. One way to deploy a Spark Connect server is to use a shell script that's conveniently included in the Spark distribution. Here's an example invocation for starting a CPU-based Spark Connect server connected to an existing standalone Spark cluster whose URI is specified in the -- master argument. The same script can be used in the case of GPU-accelerated Spark Connect, but with some additional GPU-related configs, as shown here. The new configs in the GPU case are highlighted in dark green. Notice that we're specifying 2 additional jars for the Spark Rapids ML and SQL accelerated plugins, along with some configs specifying plugin classes to invoke from these jars. And finally, there's some GPU resource-related configs that go back to Spark 3, as Gara mentioned. And not shown are possibly additional configs to control the behavior of the Spark Rapids plugin. As usual, these configs can also be specified in Spark COM files as well. Now that we have an idea of how GPU-accelerated Spark Connect works and is deployed, let's take a closer look at the innovations in Spark 4 that enabled ML over Spark Connect and acceleration thereof. So roughly, here's the state of Spark Connect before Spark 4. There was only built-in support for Spark SQL and data frames with protocol buffer message definitions for conveying SQL plans and commands, along with server-side code for handling the corresponding requests, leveraging core Spark SQL for execution. In case it wasn't clear before, the partially green Spark SQL block on the server side in this figure represents the fact that Spark Rapids Accelerator for SQL was actually supported pre-Spark 4, since its implementation, as Gara mentioned, is at the physical plan level, and it thus kicks in fully on the server side with the original Spark 3.4 variant of Spark Connect. Spark 4 developers then went on to extend the Spark Connect protocol to cover essentially all of Spark MLlib functionality. This involved defining new messages to convey ML relations like transforms, as well as ML commands like the fit command for Spark ML estimators. We saw the k-means one earlier. The Spark 4 PySpark client includes all the functionality needed to serialize and deserialize the new messages based on the application code and also the server response after execution. On the server side, a new ML handler was added that converts decoded ML protocol messages into Spark ML library invocations. Also added but not shown is the model cache we saw earlier to allow model object reuse. Finally, Spark 4 developers also added an ML backend plugin interface to allow the ML handler to instead invoke alternative implementations of Spark MLlib functionality. In the case of the NVIDIA Rapids Accelerator ML plugin, these implementations leverage GPU acceleration. Here's the ML plugin interface definition. As you can see, it's pretty simple with only one method that converts an input Spark MLlib class name to a plugin supplied alternative. Here's a portion of the Spark Rapids GPU-accelerated ML plugin. You can see the mapping of baseline Spark ML logistic regression class names to Rapids versions. The heavy lifting is done in the partially shown definition of the alternative classes that implement the plugin logic. In this case, the ones corresponding to logistic regression estimator and model. The full plugin implementation has other mappings and alternative algo implementations for the ones we support. The only requirement on the plugin implementations is that it can be invoked from Scala or Java. In the case of our plugin, actually, this initial Scala invocation hands off the full implementation to a Python C++ library that connects back to the Spark Connect Java process via Py4j to carry out the actual computations. Now let's change gears and recall why we're talking about GPUs in the first place. And it is, of course, all about the benefits of faster and cheaper processing. I'll next recap some benchmarking results similar to ones you may have seen in past presentations by our team. The first benchmark is for Spark SQL data frame processing, and is called NVIDIA Decision Support, or NDS for short. It is a slight adaptation of the TPC-DS data processing benchmark widely used in the industry. We stress that we are in no way claiming NDS-related results as official TPC-DS results, as they do not comply with the full specification. You can find the details of the NDS benchmark like how exactly it differs from TPCDS, along with code to generate data and run queries in the GitHub repo shown at the bottom of the slide. This slide has details about the Spark Yarn clusters used to obtain the results I'll show next. These clusters were deployed on the EC2 instances, depicted 8 instances in both CPU and GPU cases. The GPU instances each had one NVIDIA L4 GPU. We ran the NDS benchmark at the 10K or 10 terabyte factor with the data stored in HDFS running on these instances. These are some of the configurations provided here, mainly for future reference in case folks want to try to reproduce the results. They've been tuned respectively to optimize the CPU and GPU benchmark performance. And some of the configs you'll notice are specific to the Spark Rapids plugin, the ones starting with Spark Rapids, of course. So here are the results. The plot on the left shows running time in minutes for the CPU and GPU clusters in blue and green respectively. And the plot on the right shows the respective compute costs. We see that the GPU cluster was about 4.5 times faster than the CPU cluster and about a quarter of the cost, as measured by the EC2 instance cost per hour multiplied by the running time. The cost savings comes from the much shorter running time, despite somewhat higher per hour costs for the GPU cluster. For ML speedups, here are some somewhat less formal benchmark results, again, similar to ones we've shown in the past. This time, we ran our standard suite of ML estimator fit method micro benchmarks. They can be found in our GitHub repo linked in the slide for the Spark ML algorithms that we currently accelerate. And we ran these on a server with multiple A100 GPUs and used 2 of them for these results. Using the Spark Connect protocol with Spark 4 and both the Rapids Accelerator for ETL and ML. The only ETL in this case, though, is reading Parquet format data. So it's mostly ML acceleration. For the CPU side, we had 32 cores. The blue and green bars show execution time in seconds for the CPU and GPU cases. As you can see, there's anywhere from 5x to 70x speed up, depending on the ML algorithm, that is, which determines how much compute is happening per I/O, so to speak. Note that the y-axis is log scale. The dark green bars show the performance that would be possible if some code change was allowed for the GPU case, as we support some optimizations that Spark MLlib doesn't currently support. Okay, now switching gears again, we would like to announce the open sourcing of what we're calling a reference solution for GPU-accelerated Spark Connect. It is available on GitHub at the link shown and the corresponding QR code on the right. This is an evolving project to provide working code that captures the basics as well as best and advanced practices for GPU-accelerated Spark Connect in the sense of what we just presented. The reference solution is based on a containerized approach, placing the key building blocks, such as the user application, aka Spark Connect client, the Spark Connect server, and a Spark standalone cluster master and worker in different Docker containers orchestrated by Docker Compose. This is done to clearly illustrate the software and hardware dependencies and configs for each of these components and dependencies between these components. The repo includes the Docker files for these components, along with several application notebooks and scripts to demonstrate zero code change GPU acceleration of ML and ETL over Connect. In a bit, Gara will demo one of these. On this slide, the colored rectangles represent the 4 main containers in the reference solution. So we've got the client or application container on the left that has a Jupyter server along with the thin PySpark client for connecting to Spark Connect server and application code. The user connects to this over using a browser, VS Code, or Cursor. or some other IDE. The next one over to the right is the Spark Connect server container, which contains the Spark Connect server as a service, along with the jars and other things needed to deploy Spark Connect, as well as Spark configs. And then we've got two more containers that run the master and worker for standalone Spark. So the reference solution currently uses Spark standalone for the Spark cluster part. The green Spark worker container is the only one that maps GPU hardware and software from the host. The other service containers don't need GPU access. The executors will run in this green container. The figure shows a browser or IDE connecting to Jupyter running in the client, which connects to the Spark Connect server, which in turn launches executors on the standalone cluster worker container. Spark UI ports are also exposed to the user's browsers in addition to the Jupyter server port. The vertical dashed line represents a conceptual separation of user-managed containers and platforms on the left from what would likely be service provider managed containers on the right. Okay. Now I'd like to introduce the demo that Gera is going to show in a bit. Excuse me, losing my voice here a little bit. Okay, so the demo will showcase this reference solution by demoing the ETL and ML notebook that's in there. The notebook is adapted from another example that we've shared for some time in our Spark Rapids example repo that involved XGBoost and Fannie Mae's single family loan performance data set that's publicly available from Fannie Mae with all rights reserved by Fannie Mae. So in this demo, instead of XGBoost, the use case trains a multi-class sparse logistic regression model to predict one of 4 mortgage delinquency severity classes within the next 12-month period, given past info about the mortgage. And we switched to sparse logistic regression, because that is one of the algorithms that in Spark MLlib that our new plugin accelerates. So the ETL part basically does some windowing like operations and joins to create training examples for the ML part, which then sets up a pipeline to map the input data set onto sparse vectors with a sparse part and a dense part that are collected into single vectors using vector assembler, and then finally feeding into the logistic regression multi-class training. I will now turn it over to Gera for the demo.
Thanks, Eric. Okay, so here I have the repo that Eric just mentioned, Spark-Connect-GPU under our Spark Rapids examples open in cursor/VS Code. You can see it entails 4 services. The main part is the Spark standalone cluster represented by Spark master and Spark worker nodes. And then we have a node for running the driver for the Spark Connect server. And finally, we have the Spark Connect client that runs the Jupyter notebook server. And as Eric explained, only the Spark worker needs access to the GPU, and this basically is guaranteed by NVIDIA Container Toolkit that only this node gets this reservation. The whole demo runs on my laptop with an RTX A3000 laptop GPU. All other containers, although they share the same host in this demo, they don't have access to that GPU. And another notable part is that the Spark Connect client, which runs the notebook server, it has very thin requirements. So if you take a look, it uses the standard Jupyter notebook Docker image as the base, and on top of it, it only installs the 20 megabyte or something like that gRPC client for Apache Spark. And the other MLlib library I just use for visualizing the results. So basically, this is very lightweight. I have already pre-started the containers, so I can show you. I will be showing two sessions. So one session runs the standard Jupyter notebook in the browser. I have pre-run it already, and you can see that we connect to the Spark cluster almost the usual way. There is no visible change in the code. But if we introspect the Spark session, instead of seeing the Spark context as used by a Spark Classic session, we see a Spark Connect client connecting to the Spark Connect server and a session ID. And we can actually find that session ID in the Spark Connect server UI that I have running on this URL Spark, which is the standard driver UI interface. Yeah, so if we search, we'll find that session. I have pre-run it and it's already finished. And just to demonstrate that it ran on the CPU, I'll show you the knobs. The section showing the knobs, controlling the behavior of that notebook. And as you see, the Boolean flag for offloading the computation to GPU is false in this session. And I'll explain the rest in the second client that I'm running, which is embedded as a Jupyter extension in the cursor GPU, in the cursor ID. So the notebook starts as usual with a bunch of imports. So then we can execute this cells. So we imported the necessary packages, and this includes PySpark ML that we're highlighting is the new addition to the Connect support in Apache Spark 4.0. In this cell, we're connecting to the cluster. Again, we're getting a Spark Connect based session instead of Spark Classic. As you see, it will be the second session ID. So normally you will have a distributed file system to share data among different nodes. In this case, because everything runs on the local host, I'm cheating a little bit and simplifying the demo by sharing the directories mounted from the host in the notebook. But to clearly indicate which directories would normally be residing on a distributed file system, I prefix those variables pointing to them with the prefix global. So then, so you have, so let's make sure that we executed this. Then we have a whole paragraph defining various functions that build up that ETL process that Eric described. For in the interest of for the the only part that is interesting in this demo, that this is a massive Bushy join query with a lot of aggregations and complex expressions that we are going to demonstrate acceleration for. And as I showed in the browser-based version of that notebook, we have this knob section controlling the behavior of the notebook. So obviously in this session, I want to see GPU acceleration. That's why this flag is true. The other flags control whether we are reading raw data set, which is a CSV provided by Fannie Mae, or we initially checkpointed as a transcoded to Parquet for more efficient execution. So in this case, I'm I'm reusing the previous conversion to Parquet. And you see how this global Boolean switch maps to the way we control whether GPU acceleration is used. In the ETL case, it's a simple Boolean configuration. In the ML case, it's a mapping between MLlib classes and QML implementations. And if we don't use it, as in the browser case, the variable is simply unset. Okay, so now that we've come to the point where the whole query is built by invoking this Python functions that result in a certain data frame. And so I will just go ahead and execute all paragraphs, all cells preceding this one. Hopefully it works. See, it ran relatively fast because these were just definitions of the Python functions. The next function, the next cell should be more expensive, but it's still not as expensive as the actual query execution, because even in the Spark Connect case, execution of data frames is lazy, and so until you actually call an action to execute the query, nothing is executed on the server side. So all this time that was spent right now for a few seconds was spent on building this massive logical plan for the Bushy join query. So it's pretty big. And that's all we need to know about it in this part of the presentation. So now we're actually coming to the point where we'll execute the whole pipeline that will include ETL and ML. And while it's running, we'll show the rest of the notebook. So to demonstrate that actually something is running on the notebook, so I would like to point your attention to the right-hand side of the screen. Here I'm running the tool named NVTop. It shows the activity on my GPU. So I disregard this graphic type process on my computer and focus on the ones that will appear on the top that show the compute type. So the one that is already pre-started is the Spark Executor running in this work container, the only one that has access to the GPU. The yellow line shows GPU memory utilization at 45%, because that's what we set for this executor. And but there is no compute activity as represented by the blue line. And so when the whole pipeline runs, you will see a lot of jitter and spikes both lines. But the yellow line will spike only moderately because the ML part runs with memory allocated on top of the executor, and so you will see this when a third process joins kind of the show. So let me hit this code and execute everything in this cell and below. So now we're seeing that the actual query is running. The yellow line hasn't moved yet because we're still in the ETL part, but we see the compute activity, the blue line. So that should be done pretty soon, hopefully. Yeah, So it finished in about 30 seconds. So now we do some subsampling of that prepared data frame because my laptop GPU is not as powerful to be able to feed the whole normal data size into the ML part of the pipeline. But yeah, you see that there is now a third process, which is a Python worker that's running QML algorithms in a UDF, and everything is flattened out. So I think it basically finished. So we can now go and review the predictions, and which is not um, a little bit outside of the scope for my presentation, but we can answer questions later. So last step in this notebook is to save the runtimes and for the current session and compare to the previous session of the opposite compute, so which will be CPU in this case. And as you see, we actually see a significant acceleration in my case. Obviously, the mileage varies with the workload and the CPU and GPU types, but this is sort of what you should expect. So in this case, the acceleration factor for the ETL part was 3x, and for the ML pipeline with the logistic regression, feature hasher, and vector assembly, about 7x. So now we can actually go to back to the Spark Connect UI and look at the SQL data frame tab, and just I'll sort the queries by the duration. And as you might guess, the slower query is the one that ran on the CPU. And we can confirm this by looking at the query plan. So you see the familiar whole stage code generation execs with CPU-based operators. So there is no GPU prefix anywhere here. So that was, maybe I can even confirm this in the properties. Yeah, so Spark Rapid SQL enabled is false. But when we go and take a look at the shorter query, which is equivalent but ran on GPU. So you see that the plan is full of the operators that were offloaded to the GPU. And you might notice the major difference is that we don't have whole stage code generation for the GPU plans. And that's because the payroll overhead in the GPU plugin is low, since we operate on columnar batches throughout the query execution. Yeah, and so I think that's pretty much everything I wanted to show for this demo. So we can move to the next part. So we can share this. Yeah, so our last slide is call for action so you can try everything yourself. We have here links with QR codes pointing to our documentation. We have another notebook that runs TPCDS and that is easy to open on Google Colab, and there are free GPU instances there, so you can see a similar style of notebook where you can compare sessions in CPU and GPU mode live, and play around with it. Then we have a special repo for user tools that help you qualify your workload, which queries are most amenable to GPU acceleration. And finally, of course, there is a another repository with the Spark Rapids ML plugin. You can always reach us on GitHub and open source, or you can send us an email depicted here. And I thank you for your attention. I'm waiting for your questions.
All right, thank you, Eric and Gara. That was actually quite impressive and extensive demonstration of some of the benefits of not only be able to actually decouple the Spark Connect from the thin client to offloading all the computation on your MLlib server. I think that was quite extensive, quite involved. Let me see if you actually have any questions over here. I think I haven't seen anything so far, but as you were actually demonstrating all that, you were going through the slide, a lot of things started popping into my head. And I think one of the things that I was quite impressed was that you actually had the client that was fully blown written in Spark, in PySpark and Python. Hypothetically, if the entire same client was written in Go and it had the ability to create the same gRPC message, it would still be able to use the functionality on the other side, right?
Yeah, I think that's totally correct. Yes.
Yes, because I guess the whole premise of Spark Connect client
Right.
being in ability to actually run Spark from unknown JVM based language. So if I wrote this particular application in Go or in Rust, as long as I'm compliant in generating the unresolved gRPC plan and sending it over the Spark server, the
exactly.
execution should be identical, correct?
That's correct.
Yeah. So how is the ML plugin that you actually showed when you were executing when you were providing that as part of the plugin? Is that only executed on the Spark Connect server and the driver, or the plugin has to be executed, has to be installed, or the jars has to be installed across all the workers?
Eric, do you want to answer this?
Sure. Can you hear me?
Yeah.
Can you hear me?
Yes, we can.
So the jar is installed on the Spark Connect server container, and then that gets shipped around by Spark as usual. The actual execution involves code running in the driver as well, in the Connect server or the driver, as well as the Spark worker through executors. And the GPU part of the computation, though, is only running in the worker in the executor. There's no GPU compute happening in the driver. The only thing the driver does is sort of figure out via the plugin mechanism how to invoke the plugin. But then everything all the key compute gets handed off to the plugin.
Okay. We have a question from Sawmill. In Spark Connect, you need to specify resources. How do you handle situations where different jobs have varying resource requirements?
So I can take a stab at this. So so Spark has this ability to recognize different resource types for GPUs. You can either have a static file, or we recommend to use a GPU discovery script, which is based on NVIDIA SMI, and you can see actually that script checked in the Apache Spark repository. And so basically it's similar to other cluster management solutions, where each worker reports what they have in terms of capabilities. Sometimes you can have NVIDIA Container Toolkit help with that, but either way, so every worker advertises what hardware it has, and then the driver can schedule accordingly.
We have a question from Abraham Urib from Mexico. He's asking, he's actually writing in Spanish, so I don't know how to translate that. Abraham, would you mind translating? I actually use Google Translate, but I'll go to the other question. These jars, are they actually part of the 4.x distribution, or do I actually have to go to NVIDIA Slate to download the jars and then distribute them as part of my cluster management?
So these jars are published in Maven, Maven Central, and so
Okay.
all the usual tricks for running Spark jobs work. So you can do dash jars after downloading it locally. You can do dash packages to download it during the submission, or you can bake it into the container, as I did in my demo.
Right.
You can actually take a look at the Docker files for the build process for the reference solution that Gara demoed to see how the jars are downloaded from where and how they're packaged into the containers.
Yeah,
as an example.
Yeah, and we need some additional pip packages to run the ML part. You can see that in the demo too.
In terms of Gara, what you were actually showing, you were showing this on your laptop, which was kind of a heterogeneous container. So you had both CPUs as well as the GPUs, right? And so the driver actually knew how to execute the CPU part in the CPU accelerator and the GPU part in the GPU accelerator through the plugin, because they would assign that to the GPU base accelerator.
Right. So during the query translation process in the ETL part, it's already decided which part will run on the GPU. So that happens in the driver. And so then the plan is distributed the same way that standard Spark works.
Right. And so
and the cluster management makes sure it goes to the right workers.
Right. So in the case of, if this was running on a distributed Spark cluster, you would actually have to have a heterogeneous environment that has both CPU and GPU clusters.
Yeah, but this demo basically demonstrates it already.
Yes.
Because it has it uses a true standalone cluster to run Spark Connect server against. And to make it I guess more interesting, I could have introduced. Oh, actually, it's a good idea. I could have introduced another worker node that didn't have an access to GPU. And then we can see that the CPU-only processes go only to that node, or the other way around is actually better to see it. The GPU processes only go to worker 1 that has access to GPU, but not to worker 2 that doesn't have access to GPU.
That's true. And if you didn't have a GPU cluster, is that like a fallback mechanism, or you would actually just run on CPU with an extended amount of time because it takes too long?
So so our plugin is designed to never fail. So if we don't know how to run a query, we'll fall back to the standard CPU implementation. So you will see the plan will. So if it's a GPU enabled node, but we just haven't implemented some operator yet, you will see an extra columnar to row transition to feedback to the CPU hosted operator, and then row to columnar back if we need to continue on the GPU. But if it's just the case of like we don't know how to run it at all, or you just as in my notebook, you can turn off this property back and forth all the time. And so like as soon as you say no GPU acceleration, the whole query is not even touched by our plugin, and it will can be executed on any vanilla CPU node.
We have a question. Go ahead, Eric.
We should take, though, that as feedback that although the main point of our the reference solution is to illustrate how we do Spark Connect on GPUs, it's a fair point to sort of try to illustrate sort of best practices around heterogeneous network environment. So that's a great piece of feedback for us.
Okay. Questions from YouTube, Stealth Boy. Where do you see the GPU acceleration for big data processing going in the next few years? I mean, this is sort of more of a prediction of where GPU acceleration is going for big data processing. I mean, it's a bit of a broad question. It can apply to anything, whether you're building large data pipelines to prepare data for your AI models, or whether you're actually doing it for the traditional ML models. And if you want to take a peek at that.
Kara?
So I would like to answer from the database side, just really quickly. If you look at the last VLDB, there were like over a dozen of papers about GPU acceleration. So I think it's pretty clear that even the database industry is moving to GPU acceleration for SQL.
Eric, did you have a comment?
Yeah, I just wanted to recall Gara's first slide, maybe the second one with the
oh yeah, the growth of the graph, yeah.
Growth of data and the quotes from the press about that, and that NVIDIA feels that GPUs are a great way to address that growing need through Spark in one case.
And given that Spark now can actually run both on heterogeneous and CPU and heterogeneous environments, if you're doing large ETL processing that actually require a fair amount of number crunching, it depends on your workloads. I would add to that, right? Because the acceleration that you actually want will depend on the kind of data they actually have, and what is it the data that you're preparing for? Whether you're preparing a lot of mathematical data where you actually do require GPU accelerations, or if you're just doing text processing, in some instances you might require. If you're doing a lot of image extraction from PDFs and you're using Spark data sources to extract that, then the part that actually requires the recognition and the parsing of the images would want to be done by the CPU. So I think it depends on the use case in general. But yes, there is a growing need, as Gara pointed out, that we begin to see more and more use of that.
No, I think we'll basically argue that even traditional SQL queries, especially in the warehousing context, benefit from GPU. So it's not just about this more traditional GPU use cases with mathematical computation. It is about efficiently running joins, building hash tables, verifying and processing those fast. So that's what this query actually demonstrates.
Yes. I mean, anyway, you can actually use the vector processing to parallelize the computation. Actually makes sense to actually use that.
Yeah.
One last question before we actually end. I think this was a very incisive and a great demo to show the demonstration. Did you guys discover in using the MLlib plugin any particular algorithms in the MLlib, such as decision trees or XGBoost or regression, that did well with the plugin as opposed to others?
So I would say that kind of the main sort of rule of thumb is how much compute you're doing sort of per data point. And the more, the better for GPUs to sort of compensate for certain overheads in getting data into the GPUs and so forth. So like k-means with large dimension, large number of clusters, a lot of iterations is a great one. We showed logistic regression with multi-class. Another great scenario. Like, the more iterations are required, certainly the better. There's more compute for, the data that you've loaded onto the GPU as you do more iterations. So that's what I would, kind of as a rule of thumb, throw out there. Yeah, I did want to, for the previous question, I did want to point out one of the links that Sarah showed on the last slide is to a tool that actually can be used to sort of, from a CPU run, get a pretty good idea, prediction, estimate of GPU speed up based on actually ML modeling. So, if that is a concern for folks, we are building tools around issues like that.
Great. I think on that note, thanks a lot for your brilliant presentation and your contributions to Apache Spark, especially with this particular addition to ML, Spark ML running on Spark Connect. It actually brings and extends the power of Spark to be able to use both heterogeneous environments. So thank you, Gara. Thank you, Eric. And thank you, Carly in the background. And thank you all for joining us. And the recording of this will be available for you on our Spark channel. So feel free to share. And then don't forget, if you are local in the Bay Area, do come and attend our Spark Happy Hour on November the 13th. There was a slide on the previous presentation when we started how to actually register. So